Hey there. Welcome everybody. So today I want to give a good introduction to assignment 3, go through it problem by problem and talk about a few points and maybe give a few tips and hints to help you out because it's a big one. So then once we are done with assignment 3 in this lecture, I want to do a little bit of a review for the midterm. I did post a review sheet that gives bullet points, so I'll go through those point by point and just say a few words. It is the exam is over everything we've done in the course so far that has been reflected in an assignment. So ellipse, and with the addition of there may be some ellipsoid geometry, but we'll talk about that when we get to that. So geodesy assignment 3. The first problem is an easy 5 points. I really want people to feel comfortable using the spreadsheet to calculate their angle conversions. And the reason for that is because angle conversions are exact. So any decimal places that you truncate when you are calculating with radians, so if you only include 3, 4, 5 decimal places, you're severely introducing error that will propagate through your computations. And propagate meaning we know what propagate is, just like errors in a traverse. We propagate truncation errors or rounding errors through the more computations we make, the larger that propagation gets, right? So problem 1, all you need to do is make sure you have that HDD to HMS worksheet downloaded. And I should probably size this to make sense to you. There we go. And you can create a spreadsheet however you like. This is just a suggestion or an idea. So angle conversions, if you make something like this, the nice thing is you can just copy and paste. And then you can say 0.1, for example, and then you could get, I don't know, fancy and not fancy, but just to make it easier, you can go this point number equals that one plus 1, so that'll be a 2. Now, as we copy and paste, that will fill in. And you'll see we have 0.3, 0.4, because it's using that formula. Some of you are not really comfortable yet with Excel, but I strongly encourage you to become comfortable because going forward in your future courses, there is a lot of Excel work. So there's 10 points, which is what you're asked to do. And you can just make up some latitude and longitude or go to Google Earth and pick some points, where you're from, maybe pick a point there. But I'm just going to go, here's 42.3554, and these are DMS, and minus 121.5524. Notice that none of my minutes or seconds are more than 60. So, don't just start typing out a bunch of numbers because we have to adhere to the sexagesimal system, right? That's what DMS is in that 60 base number system. And then you can go equals, convert it to decimal degrees equals HMS to HDD. And this is some VBA code behind the Excel spreadsheet, and then you just drag that down, and it's going to drag the function down, not the value. So it's going, whereas this one represents that cell. This one is, since we dragged it down, it's representing the longitude cell. And then convert it to radians. Now what you can do is just drag that down, and I'm going to just copy these. Remember, I'm just copying the formula, and I can just paste it into these, right? Actually, before I do that, I want to format it so it makes sense. So I'm thinking I'm going to I'll make them all centered, and of course latitude and longitude. If you go to your number formats, you can use the degree minute second format, and for decimal degrees, use the decimal degree format. If you don't have them in the spreadsheet, I went over at the beginning of the term how to create those. If you want to create those and you don't know how, just reach out and I can help you, or probably anybody can help you that knows Excel. It's super easy to do. There we go. So now I'm just going to copy that and paste them so that whatever I type into those latitude and longitude DMS columns is going to be converted, because I'm just pasting all these functions. And another thing you can do is, I don't want to go to each cell and go to the custom and format those cells for DMS. So another little tip is, if you copy the cells, then you can paste. If you right click and just go to the little paintbrush here, it'll just paste the formatting. So it'll just paste the degrees, minutes, seconds format, not the number. And I'll just do one more. So now when I type these in, let's see, I'll make this 44.2531, and you see the formatting's there. The conversion's filling nicely. So this problem one is it's just a gimme. It's an easy 5 points. So you can almost think of it like extra credit. Anyway, so that's problem one. And, use colors where you want to, design your own spreadsheet, all that. Problem two is a biggie. And it's problem two, but it's something we've done before. It's not new. We did this in the spherical environment, and so in this case, we're going to do the same thing, but in the ellipsoidal environment, and apply those ellipsoid functions that we've developed. So a 1 to 24,000 USGS topographic quadrangle covers 7.5 by 7.5 minutes. And again, we're going with the lower right hand or the southeast corner of the map, and giving it coordinates lambda equals 100 degrees east longitude. So make sure that you are, I'm going to highlight that. So make sure you work with these coordinates accordingly. And if you're more comfortable looking at longitude as west longitude, so that you add the 7.5 minutes for, if you work with east longitude, that you have to draw it out. Think about what you remember. So west longitudes they increase going, I make sure I say it clockwise if you're looking down at the Earth. East longitude increases going counterclockwise. So it is always helpful to sketch these out and say, okay, do I need to add the 7.5 minutes or subtract it to get my my other corners? So lambda equals 100 degrees east longitude, psi is 60 degrees north longitude. And we're going to use the Clark ellipsoid. Why? Well, because that's what is used for, that's what USGS uses actually for the topographic maps. So a little behind the times, but they're just ellipsoid definitions, and they're all equally valid. So we're going to use the Clark 1866 ellipsoid. So you'll have to look up the semi-major and semi-minor axes. I've given them in class before. You can Google. So yeah, get your A and B for the north and south, or for the semi-major, semi-minor axes. And we're going to compute the ellipsoidal dimensions first. And we're going to find the length of the north line, the length of the south line. And just like in the spherical case, we're going to need to calculate the radius of the parallel of latitude, because we're looking for the length along the parallel, right? And that is slightly different, we discovered, with ellipsoids. So I'll just write out here, recall how that n value, and also recall that RP is equal to n times the cosine of the latitude. And that's the wrong symbol. We've been using phi, not theta. So n times the cosine of the latitude, and then we multiply that by delta lambda, or the 7.5 minutes in this case, right? To get those. Not too tough. And my biggest tip for this problem 2 that has a ton of parts, there's a lot going on with problem 2, just take it bit by bit. Do it in a stepwise fashion. Calculate the length of the north line first. And as you do that, go through and say, okay, well, what do I need to do in order to get the length of the north line? Then apply it to the south line. Then we're going to go to the, just make a little comment. What types of arcs are the north and south lines? That should be available to your audience, right? And then the length of the east and west lines. Remember, the east and west lines are along the lines of longitude, and we know what kind of arcs those are, what kind of arc distances those are. And remember also that unlike the length along the parallel of latitude, the length along the longitude are going to be equal for the east and west line. Not true for the north and south lines, right? The north line, and you can see this if you draw it out, the north line is smaller or shorter than the south line because of that convergence of meridians, right? And then you'll want to state what types of arcs the east and west lines, and the length of the geodesic from the southwest to the northeast corner. The geodesic, remember, is it's analogous to the great circle distance. It's the shortest distance on an ellipsoid between 2 points. So we're going to come up with the length of the geodesic, the shortest length on the ellipsoid between the southwest and the northeast corner. We're going to use NGS to do that. Let me demonstrate. I'm going to demonstrate. So if you bring up Google, and if you're wondering why I don't just maximize this instead of dragging the sides out, it's because my video recording screen is actually smaller than my computer monitor screen. And that's on purpose. I could make it full size, but sometimes I like to have things off to the side. Anyway, just a little aside. So if you type in NGS Toolkit and go to it, you have all these tools, remember? And the tool we want is the inverse, forward, inverse 3D, forward 3D, the third one down in the right column. So we click on that, and we have all these tools down here. We want to use the third one down in this first set, forward, inverse. Let's see, can't really see all that, can you? So this actually calculates that geodesic line for you. So that should be rather pleasant for you to hear. And if you just click on Clark 1866 ellipsoid, then it bypasses this other ellipsoid drop down. So it doesn't matter that it says Area 1858, that's default, but we have Clark 1866, and the next boxes are, you can define your own ellipsoid, which is fun to play with, actually. And let's say we go to the first one, we call it Southwest, and I'm just going to type in a latitude to give you the how we format this, and it's going to be N 60 space 00 space 00, and you have to put a decimal in or it won't. I just put 5 zeros there. You have to do the decimal or you'll get an error. And then we have west longitude, I'll say 120 00 space 00 point 0000 consistency. So that's the first one, and we know the latitudes and longitudes of the point work of the four corners of the map. So let's see, second station data. We'll call that one northeast, and I'm going to say it has a, let's see, a north. I'll do something different. 60 20 00.0000, and I'll say west 120 point, or not point, space 00, let me give it 10 space 00.0000. Okay, compute azimuth and distance, push the button, and you get a result. And this gives all the information you put in. It gives the A and B of the Clark 1866 ellipsoid. It gives you the forward azimuth, which that's good to know. That's good. You can use this tool to check some of your azimuths and that sort of thing. It gives the back azimuth. As we can see, they are not equal. And the ellipsoid distance is what we're wanting to capture from this. And the best way to do that is to use the snipping tool. I'm a Windows user, so I'm not sure what the Apple equivalent would be in the iWorld, but Windows uses a snipping tool. So what I do is I just capture that, and it will save it as an image. And then you can save that image and paste it right into your Excel spreadsheet for, as a reference. And then you can, of course, type out the ellipsoidal distance in your solution portion. So that's the NGS toolkit for, or the NGS tool for calculating ellipsoid distance. So that's what we're going to do there. And then we're just going to recreate what we did in the second assignment, where we used the spherical Earth model with the radius of our spherical Earth model being 6,371,000 meters. And then you're going to make a table comparing the lengths of each line, the areas, and with the lengths of each line, that's all four sides, or really three, since the north and south are the same, or the east and west are the same. And the diagonal, the ellipsoidal distance between the southwest and northeast corner, you're going to make a table comparing those distances. And it would be nice to see some relative error difference, the 1 in 10,000 or 1 in 20,000 or whatever you come up with for each line distance. So that's problem 2. And I did provide a template. Again, I'm going to have to shrink this. Bigify. Okay. So this is the template, and the P2 quadrangle tab is really just where the solution. It's just sort of the solutions, the summary of where your computations. That's one way you could do it. You could also rearrange this. These templates are suggestions, but they're very nice suggestions. I think you should use them. It helps me grade when you use them. But here is the same template wherein, where'd it go? I added some stuff for my computations. And you can do it that way if you like, or you could use the separate sheet. A couple things I want to point out. So I have, there's certain information you're going to need to do your calculations, right? You're going to need this MNRP, that S phi, which was the meridional arc distance from the equator up to each of our corners. And remember, we used a right quantity and a left quantity. So you could do that in the same spreadsheet. And here I have my output from the inverse tool on NGS, and then all your solutions. So the template has, go away. The template actually has a separate tab. And what's really nice is there are examples here that you can try to reproduce the numbers. Oh, before I go on, let me give you another quick tip. So see here how I've put my formula in here. So all my formulae are there that I'm using for this problem. And I've actually built a library of these equations. You can use the equation editor in Excel or Word to build these equations, but I hate working with the equation editor. I think it's really cumbersome. It takes a while if I'm going to build a lot of these. So once I have an equation built, I use that snipping tool, and I take a screenshot. I take a snip of the equation, then I save it in a library of equations. Then when I go to build a spreadsheet in which I want to show the equations I'm using, I just insert by going, here, if I go up here to insert, picture from this device, and then here's all these, I can just grab what I want and add them in there and insert. And then you have them all. If you create a library of these, then it's super easy to add these. I mean, you could also handwrite them and scan them in and then cut them into separate ones, because you should only be showing the equations that you're using in the spreadsheet, not like a whole sheet of equations. So that's just a little tip. So I have all my ellipsoidal formulae here, and then also ellipsoidal formulae, but I have, this is that infinite series expansion to get our G, our meridional arc length. So that's another little tip. But this, these examples, so the red tabs on the bottom of the template, there's meridian example and meridian comps and area example. You can actually, right next to these examples, build exactly the same thing and use my numbers here from the example to try to recreate what it is you are trying to calculate. And that way you're not getting to the end of these huge, because these are pretty big, particularly the G calculations, the S2 minus S1. Calculating the S's takes quite a bit of work. But what this spreadsheet does is it separates it out so that you have all the parts and pieces, and then you can just add them together to get your S values. So yeah, that. So you can use the same thing. It's an example. You can build exactly what you see and try to get your formulae to produce the same values that you see in the example. And then you can just copy and paste all of the cells that you reproduce into your meridian comps, and then just reference everything in your title sheet for the problem. So a lot to number 2, but I think these tools will really help you. Like I said, just be sure you're just taking little bite-sized pieces, and don't get overwhelmed by, oh my gosh, I have to calculate this. I don't know where to start. Well, just start at the beginning. Do one thing at a time. That's why these are built this way, is so that I'm trying to give you a way of not just going through the bits and pieces, but how they go together and how to present then a nice looking spreadsheet that could be used even as a calculator for ellipsoidal parameters. So that's number 2. And then you have the spherical Earth model, and then what you'll do is you'll build a table that will compare them. Like I said, I like to show a relative error column. So anyway, yep, there's the template. Go away. Go. All right, so that's problem 2. Problem 3 is some coordinate transformations. You're given geodetic coordinates. So 3 and 4 are both coordinate transformations. We have not yet looked at calculating the LGH coordinates, local geodetic horizon coordinates, ENU, easting, northing, up. But we have done the XYZ, the phi lambda height coordinates. So you could go ahead and do those. And after the exam, we'll start looking at calculating the LGH coordinates. So you have that in your toolbox for doing these problems. The key thing about these problems is read them super carefully. Do not just glance at these words, because as we discovered when we were first exploring coordinate transformations, you have to keep your perspective. You have to know which coordinates are in which system, and these problems come at the transformations from different directions. So be super, super careful that you are getting your coordinate systems correct. And the best advice for that, I know I say it all the time, but sketch it out. Sketch, and label the points with what you're given here, and it'll make it much easier to look at that diagram and say, oh, okay, I need the origin of my old system, but I need the coordinates to be in the new system. And since I'm translating this direction, those coordinates should be negative. Or, you can use that kind of analysis to make sure that you're going in the right direction. So draw a picture. And don't get overwhelmed by old coordinates, new system, new origin, old coordinates. Just go slow, be careful, okay? So yeah, number 3, we can certainly do the XYZ and the latitude, longitude, and height of points A, B, and C, and then just be ready when we go over the LGH coordinates to plop those formulae in. Number 4, very similar, but with a little bit of difference. You're going to be scaling I'm just going to say you're changing your units. You're going from metric to international feet. So be aware of that. You're going to be moving in a different direction than in number 3, but essentially just a different perspective on the same types of problems. Okay, number 5. The following table points are defined in the 2D. So this is just a 2D rotation and translation, which we went over. So that should be familiar to you. Shouldn't be too tough. You can think of these coordinates as math coordinates, and just treat them accordingly. Okay, and then I posted with this assignment a couple of articles that you can read and answer some questions. The discussion, I try I try to enrichen the content, all the math content that we're doing, with some just some human interest articles. So they're a quick read. They're a quick read. You can print them out, make notes, highlight, and then provide the discussions around each of the articles for 7 and 8. And problem 6, this comes straight out of the book. The book goes into detail about the advantages and disadvantages. So rather than just copy and paste, read through, think about them. You know, what in what situations would LGH, geocentric, and geodetic coordinates be best for? So anyway, and in 9, the usual, discuss anything. I like to the things that I pull out and use for developing these assignments or evolving them. I ask for difficulties you encountered, suggestions for improvement, but that's not all you need to put in there. You can certainly put other comments as well. This was really interesting to me, or I hated this because, or, and most of you are really doing a nice job of giving me detailed discussions, and I appreciate it. I read them, and I do make notes, and I do evolve these assignments from year to year. So even though those discussions don't help you this year, they're going to help the next course. So anyway, that's assignment 3. It takes some time, so don't put it off. Hopefully you started on it already and have at least read through and become familiar and looked at the things that you know how to do and don't know how to do. And so email me questions. You guys can call me. You can text me. I put my number on the syllabus, so there's lots of ways of reaching me, and I will respond, I promise, in a timely fashion. I also want to reiterate that I understand there are some students who cannot attend the Zoom sessions that are scheduled weekly, but to those students, I'm inviting you to contact me and say, hey, can we do a Zoom session on Wednesday night? And we can schedule them week by week. And I'm happy to do that. It's nice if you can get a group of people together for a Zoom session, but if it's just you, then it's just you. That's fine. I'll do that. I enjoy having the Zoom discussions. So don't be afraid to ask for some time. I will grant it. I promise. Okay, so that's assignment 3. I think once you get going on it, it's not going to be that, it's going to be time consuming, but it's not going to be that bad. It's not going to be that difficult because we have all of the equations to work with, right? Okay, exam 1. I just want to go over a few of these points and talk about exactly what I posted on Canvas for the exam review. You'll see that it is indicative of what we've talked about so far this term. And I want to point out that exam 1 review, these points, how did I put that? Each of these, so come on, I want to draw. The exam may include any of these points, or I'll say concepts. The word point has too many meanings. So any of these concepts, but not necessarily. And I mean not necessarily. I'm not gonna be able to fit it all in there. I don't think. Maybe. So all of these concepts on this sheet are from our work this term. Don't assume that just because they're on this sheet that every single thing on here is going to be hit by the exam. but it will further your understanding if you go through each point and understand what we're doing. Okay, so let's see. Why do we take these stupid exams? Well, one is it exams help us to get all on the same page. Students progress at different rates, and by the time of midterm, we should all be at the same place so we can move forward. So it does that. It reinforces your understanding of the concepts when you study for these exams. Let's see. Exams actually require you to demonstrate critical thinking skills, because the questions on the exam are not always necessarily like homework problems. There are different approaches to the concepts we've talked about. So no fair giving me a criticism, well, we didn't have a homework assignment like that. Well, the exam is for you to put the ideas together and come up with solutions. So let's see, exam problems may be just like homework, use different geometry. They may use different geometry than the homework to determine understanding of concepts. Ask you to draw a sketch and show the necessary computations. And so the actual answer is not the important thing. The important thing in this academic coursework is to be able to demonstrate the process. So a lot of times questions will be worded like, don't solve this problem, don't do any computations. I want to know the steps. There may be some problems that ask you to generalize a process. So be aware of that and be clear. So let's see, where did I leave out? Where am I? Oh, require a basic derivation, demonstration, understanding of concepts. Okay, I just talked about that. So the summary of course material, quantity, always show units. So always. So that means degree, minute, second symbols, degree symbols, meters, international feet, U.S. survey feet, inches, miles, kilometers, whatever. Where'd my pen go? And since I'm going to be writing on this, I'm going to bigify it. Okay, that's better. Always show units. Use industry standard units and precision. So that would be, 3 decimal places for meters. 2 decimals for feet. Industry standard, always present, always. Or angles are always in. You got it, DMS. If I see an exam and you're providing a solution in radians, unless it asks you to show radians, then I'm just not even I'm not gonna go to the trouble of converting it, and I'm just gonna count it wrong. So remember, we're presenting these things. So angular units, sexagesimal system, that's the base 60. And used for DMS. Radians, we know what those are, Gauss, mils, and milliarc seconds. We went over those at the beginning of the term, so just understanding the definitions and how to convert the different types of angles to other angles. Let's see, U.S. survey foot and international foot. I'm going to spend a little bit of time here. There seems to be confusion about which conversion factor to use for U.S. survey feet and international feet. I think that there are some people, and it's not just this course, but there are some people who just don't care. Like they think they're the same, or They're definitely not. I mean, granted, we have to go out quite a distance to see the difference in them. I think it's like 2/10 of a foot in 100,000 feet or something like that. It's not a lot, but they are different. So make sure you are familiar with the two different conversions. So US survey feet, I'm just going to do it right here. US feet. There are 39.37 inches in a meter. And of course, there's always 12 inches in a foot. So that's I've seen this a lot, people using that to using that conversion factor when they're supposed to be providing international feet. Now think of how big some of those values are that we come up with. The ellipsoidal area, those are huge numbers, and you're going to see the difference between square US feet and square international feet. The international foot, I'll just say I foot. That is the 0.3048 meters per foot. And those are not the same number. They're slightly different, but they are different. I'm really emphasizing this because there's been a lot of trouble throughout many courses with students understanding that they're two different things. Don't even think of them as the same as feet. Think of them as meters versus, I don't know, miles, or, US survey feet and international feet are not the same thing. You need to care about and understand the difference. And then meter, we know what a meter is. Let's see, mathematical models, appropriate applications. So that means that knowing when to use which model. Flat Earth, that's a plane. So the flat Earth is Euclidean geometry. That means that all of our geometric axioms are at play. We have a spherical Earth model, which is non-Euclidean. So I'll say this is EU for Euclidean, and non-Euclidean, non-EU, and constant radius. The ellipsoid of revolution, ellipsoidal geometry, also non-Euclidean. I have a little guy that keeps appearing. It's driving me nuts. Okay. Also non-Euclidean. Only 4 of our axioms, our Euclidean axioms, are at play. And for this, we have A and B, which are the semi-major, semi-minor axes. We have flattening. We have eccentricity and eccentricity squared. This is a varying radius. Varying radius. The radius of the ellipse decreases from the plane of the equator up to the pole, right? Varying radius. Okay. Let's see. Also in the beginning of the term, we talked about the different branches of geodesy: geometrical, physical, celestial, satellite. And we've also gone over several different latitudes. There's geocentric and geodetic and reduced. And those are not the only latitudes there are. There are lots of different kinds of latitudes. But those 3 for sure, be familiar with how they're constructed and be able to sketch them. If asked, demonstrate a reduced latitude. You should know that. You should also know the conventional symbols we use, the beta, psi, phi, and which one goes for which. Again, this course has, much like any higher level engineering course, tons of formulae, tons of symbols. A lot of the symbols and letters are reused for different things. So you have to be able to understand the contextual use of the symbols. Okay, normal sections. We defined what a normal section was early in the term. And let's see and then what that looks like for the spherical Earth model, ellipsoidal Earth model. Let's see, time and dates, that's pretty easy. Know those definitions. Spherical triangle solution. Great tools, great tools. Know how to work with these and when to use which in which kinds of situations. How to calculate using those sines and cosine laws to calculate the azimuth of a line, and then use those to calculate azimuth. We did that. We did length of a line, or length of an arc. Those are some applications that we've used the sine and cosine law for. Okay, next, azimuth of a line from solar or stellar observation. If there is something on the exam, it's not going to be any more complex than what we did on the homework. So just the basic fundamental principle of the azimuth of a line from a solar observation. Great circle distance. Know that. And I'm just going to put another little bullet point here. A parallel of, let's see, I don't want to put it that way. I'm going to put m psi is arc distance along a parallel, and what kind of arcs those are. All right, distance, surface and chord. So you need to know the radius of a parallel, the difference between and how to explain what a great circle and a small circle are in terms of, planes intersecting spheres, and how you would come up with the radius of each. 3D chord, we've done that ad nauseum. That's just the distance formula, right? Meridian arc, we've been talking about that. Parallel arc, normal lines and sections. We talked about that in the very beginning of the term. A geodesic line, we did go over that. So know the concept of a geodesic line. You won't have to calculate the length of a geodesic line because we haven't gone over that. And I don't think we will go any further than just using the NGS toolkit for that. So area, know that there's a difference between a planar area, a spherical area, and an ellipsoid area, and know the method by which we get the calculations of each. Okay. Direction of a line, azimuth and bearing. So we have a flat Earth model or plane, like on a map. So we call that grid azimuth or grid bearing. We have a spherical Earth model. We calculated azimuth on that. And that's where we use sine and cosine laws, right? The ellipsoidal Earth model, how to calculate basically the concepts, not really so much the calculation, but the concepts of azimuth and bearing on the ellipsoidal Earth, and convergence of meridians, of course. We've spent quite a bit of time on that. And then lastly, understand the difference between the different coordinate systems we've talked about this term. We've talked about the geodetic coordinate system, the geocentric coordinate system. I keep crossing out my words, so I'm trying to underline them. Local geodetic horizon, that's the ENU. Astronomic, And know the definitions and what mathematical models go with each of those. Okay? So, that was a great little synopsis of what we've done this term, I think. But if you're familiar with these concepts in these ways, you should do great on the exam. It's not that difficult of an exam, but it will require thought. There are no gimmies, so well, there might be one gimme, but anyway, good luck, and hopefully the introduction to assignment 3 was helpful. And we will not, of course, have, I will not be putting out a lecture for the day of the midterm. So anyway, study away and nail the exam. I'll talk to you later.